Good afternoon, everyone. My name is Haiping. I come from ByteDance and Fudan University. It's my great pleasure to present our work, Medley. Today, I will walk you through a real scaling problem in the commercial live streaming CDN system. And let's first start with the background of live streaming, or the LVS has deeply penetrated every corner of our daily life. We use it for the personal live sharing, live e-commerce shopping, competitive gaming. All of these services will generate massive real-time video traffic that must be delivered reliably to users all over the world. And to support such large-scale and low-latency delivery, the live streaming platform must rely on the global CDN infrastructure. However, this massive scale also brings a serve and growing challenge for the platform. That is the cost of the bandwidth. And because in a typical live streaming CDN infrastructure, the video data will flow from the source through the CDN nodes and finally reach the end users. And every bit of data that's flow inside and outside the CDN nodes will translate directly into the real financial cost. For large commercial providers, the bandwidth expansion has grown into a dominant and heavy financial burden. Traditionally, the operators often focus on optimizing the egress bandwidth, which is the traffic sent to the users. However, in our large-scale production environment, we have discovered another traffic component that also contributes enormously to the total cost. That is the Midgress bandwidth. As shown in the left picture, the Midgress refers to the internal cache traffic between the CDN nodes, which including the traffic from the source to the reflector nodes and from the reflector node to the end nodes. And this internal traffic do not directly serve users. However, it's very essential for caching and distribution. To qualify this impact, we have defined a key metric, that is the MER, which equals to the midgress bandwidth divided by the egress bandwidth. And our measurements shown that in our production, the common DNS-based scheduling, the midgress ratio will reach as high as 41%. And even with a shorter redirection strategy, this ratio is still 23%. And this number has clearly indicated that the midgress traffic has become a major cost bottleneck in our production CDN system. So where does all this midgress waste come from? The first root cause is that despite users' request, most live CDNs will use the local first DNS scheduling, which will direct the users to their geographically nearest end node. While this seems intuitive, it actually scatters the viewers of a single live channel across dozens of edge nodes. As shown in our example in the right, one channel can easily spread to over 50 nodes at the same time. And each of these nodes must pull and cache the entire video stream from the up-level nodes. And our production trace has also confirmed that the DNS-induced request dispersion directly leads to sustainable and unnecessary midgress traffic. To elastically scale the resource to support our fast-growing and global distributed viewers, the modern commercial CDN system now have deployed a mix of large core clusters and numerous small edge nodes. And this is a very heterogeneous node architecture, which directly exacerbates the midgress waste. The large core cluster, it has the sufficient resource and can share the internal cache efficiently, so they usually generate relative low midgress traffic. However, the small edge node, which have very limited capacity and cannot share the cache with each other, and it can dramatically increase the midgress traffic. The rapid growth of the small edge cluster to improve the system coverage makes this Midgress problem even worse. And a natural question is, why not we just redirect all the user requests to fewer nodes? As shown in the left, the redirection works by consolidating all some user requests from low utilization node to fewer high capacity nodes. Thus, it's reducing the number of subscribing nodes. However, this approach has fundamental limitation in a large heterogeneous CDN. Our CDN has nearly 1 million nodes with highly diverse capacity, and most small clusters simply cannot have enough spiral capacity to absorb the large number of redirect traffic. And in our real-world deployment, the redirection can only affect nearly 60 of user requests, and the remaining traffic will still suffer from the significant Midgress traffic. So we need a fundamentally new design. And let's rethink the problem. The Midgress cost can be expressed with a very simple formula. That is, the Midgress cost equals to the number of subscribing nodes multiplied by the Midgress size per node. All the related world, they only try to reduce the number of subscribing nodes. But the system is highly dynamic in user requests and resource, and it's really hard to optimize the Midgress waste. So we ask a new question. What if we shrink the data each node needs to pull, and not only fewer nodes, but less data per node? And that is the insights that gave birth to Medley. And here is our magic. We split the video stream into K substream. In the old way, every node will cache the full stream, and with Medley, each node only cache 1 over K of the total stream, and where K is the number of substream. In the example we show here, the default strategy will generate 3F Midgress traffic, where F is the video bitrate, and each node cache a full stream to serve the local users. But with the 3 substream method, and the video is split into 3 substreams, each node will only cache 1 over 3 video contents, and the total Midgress will jump directly from 3F to only 1F. But at the same time, to recover the original video, the user needs to pull different substream contents from each node and reassemble the video locally. And in general, using K substream splitting model, the Midgress can be reduced to almost 1 over K of the original cost. And this is a game-changing approach for the Midgress optimization, because with a sufficient large value of K, we can minimize the Midgress traffic without being limited by the node cluster or the limitation of traditional redirection mechanism. That's all about the idea of Medley. But to realize this idea, we need to re-architect the entire live CDN system to support the substream-based delivery. And Medley addresses these core technical challenges. The first, we need to decide how to determine the optimal number of substring, that is the K, because it's very important to the total cost as the system overhead. And second, when the node split the video into substring, what frame partition strategy do we need to ensure the load balance across substring? Third, how to transmit the substrings from multiple nodes without compressing the user KOE. And in following slides, I will explain each challenge and our solutions in details. First, how many substrings do we need to split? The core principle of substreaming is to control the number of substring K. A larger K will reduce the Midgress, but it will also introduce higher system overhead, including the increased scheduling complexity and client-side coordination. But a smaller K will reduce the overhead, but also yield lower cost savings. And to balance this critical trade-off, we design a utility function that integrates three key factors: the Midgress reduction gain, operation overhead, and the system robustness. And guided by the real-time network condition and node load, the CDN scheduler will dynamically scale K up or down to maximize the overall utility. And as shown in this example, the channel initially split into two substreams. And when the viewer count declines, the system will scale down to one substream, keep the Midgress savings, but it minimizes unnecessary overhead. When the viewer number increases, the system will scale up to 4 substreams to maximize the Midgress reduction. And this adaptive mechanism will ensure Medley works stable on the device life scenario. And second, we also address the challenge of smoothly distributing the video frames across substream. Traditional scheduler will often result in serve problems, either substream traffic overload or frame starvation, and both of which will directly impair the playback smoothly. And let's first examine the load imbalance problem caused by the native round-robin. When an incoming video stream is split into 2 substreams using the round-robin, and all F-frames will be located into the first substream. And given that the I-frames are significantly larger than the other frame type, the substream 1 will quickly become the traffic overload. And if we instead use the weighted round-robin, widely alternative that assign the frames to the substring with the smaller current traffic volume, a different problem will also emerge because the I frame can be up to 10 times larger than a typical P frame. Assigning one I frame to the first substring will force it to wait a very long time before it's receiving the next frame until the substring 2 accumulated the sufficient data to balance the load. And this also leads to serve frame starvation on substring 1. And the solution we use is to jointly account both frame type and frame size to a hybrid scheduler, which can combine the advantage of both schedulers. And the final challenge we consider is how to transmit more better. Critical problems in substring delivery is the substring blocking, which will directly cause the playback stalls and might degrade the user experience. As shown in this example, we can consider a client that reconstructs the video from 3 parallel substreams, and each will mark in a different color. If the network part for the substring 1 gets poor connectivity or packet loss, the decoder will be stored and experience the delayed first frame. And this will directly harming the user experience. To solve this problem, Medley introduced 2 solutions. The first one is the first gulp oscillation. We will retrieve the first gulp using the full stream mode and to minimize the startup latency, and after which the client will smoothly transition to the substring delivery. And we also provide the fast frame request, which can detect the user when it's suffer from the substring block and proactively fetching the missing frames from the alternative nodes. And let's look at our production environment. We have deployed Medley in ByteDance global live streaming platform and conduct A/B experiments over 3 months. And the system run in real production with average ping traffic up to 10 TB per second and serve up to nearly 1 million concurrent users. We have compared the Medley with the DNS and the redirection scheduling strategy. And the results are really striking. The Medley achieved nearly 86% of the cost reduction compared to the DNS, and almost 76% compared with the redirection. We have also measured the key business and end-user engagement metric, including the total watch duration and purchase behavior. And this result also proved that the Medley can achieve the massive cost reduction without any degradation to user experience or business metric. And to conclude, we have 3 takeaways. The first is through the measurements, we identify the Midgress bandwidth as a major cost bottleneck in the modern CDN. And second, we also propose the Medley, which a novel substring splitting architecture. Third, our production deployments also show that Medley reduced the Midgress cost by up to 86%. And we believe Medley provide a practical, scalable, and cost-effective solution for the modern live streaming CDNs. Thank you very much for your attention. I'm ready to take any questions.